Hi everybody, and welcome to the latest in our series of gas law videos. This time we're talking about the combined gas law. And as the name would suggest, this is a law that we would use essentially by combining the three laws that we've learned so far. For each of the laws that we've learned so far, we've held one quantity constant, either pressure, volume, or temperature. In this case, we're looking at a situation in which all three variables change. The equation for the combined gas law is what you see right here. And you'll notice that there are elements of all the gas laws in that equation. And if you were to cross out one of those variables, for instance, both pressures, by holding them constant, then essentially you would end up with Charles' law. And so if you eliminate the variables that are constant, you can use this combined gas law for any of the problems that we've encountered so far. A couple quick reminders. Your temperature in these gas law equations, anytime you're dealing with temperature, should always be in Kelvin. And to get the Kelvin temperature, you take the temperature in degrees Celsius and you add 273. And then if you need to deal with pressure and volume, you have to make sure you use the same units for pressure and volume on both sides. So, for example, if you're asked to calculate the volume, and the volume on one side is in milliliters, then you should make sure that your volume is given in milliliters on the other side. So, just a quick reminder of those things, and now we're on to a sample problem. So, here's our problem here. We have 500 liters of a gas in a flexible walled container, and we're preparing it at 700 millimeters of mercury. That's a little less than the normal atmospheric pressure, and 200 degrees Celsius, which is pretty hot. The gas is placed in a tank under high pressure. When the tank cools to 20 degrees Celsius, the pressure of the gas is 22,800 millimeters of mercury. So we're jacking up the pressure. This would be typical of the process that you would do preparing an oxygen tank or a scuba tank or something like that. And what we're asking is, what is the new volume of the gas? So, what we've got here, as always, I like to set up our problem to make sure that we have all of our variables and then we know what we're solving for. So, we're going to use 700 millimeters of mercury as P1 here. Then we're going to fill in V1 as 500 liters. That's the very first thing we see in the problem. And so we know that our answer should be in liters on the other side because we're solving for volume. And T1, we're going to take that first temperature of 200 degrees Celsius, we're going to add 273, and we're going to end up with a value of 473 Kelvin. Now P2, once we change the pressure, we're changing it to 22,800 millimeters of mercury. I know it's a big number. I actually had to convert it from the original problem, but that is, again, typical of the process that you would use to make a tank of pressurized gas. And we know that we're solving for the volume because it asks what is the new volume, so we don't know V2 yet. And we do know that T2 is 293 Kelvin, which is what we get when we add 20 plus 273. Okay, so now we've set up our problem, and what I've done on the next page, just to kind of help this video flow a little bit, I've learned my lesson from previous videos, is I've already set up the problem here. And so on one side we have P1 times V1, 700 times 500, divided by T1, which is 473. And on the other side we have the final pressure, P2, which is 22,800. We have V2 on top, and we divide all of that by T2, which is 293. So, as always, when we have a proportion, when we have two fractions, we have to cross-multiply to solve. And so we have 700 times 500 times 293 on one side, and 473 times 22,800 times V2 on the other side. And you can look above to see where I got those values. And so what we end up with is two very big numbers on either side, and what we're going to do is we're going to divide that big number on the left, 102,550,000, by the big number on the right, 10,784,400, and we're going to divide both sides by that very large number, And when we do that, we're going to get v2 by itself, which is always the goal. When we solve for a variable, we're always trying to get it to be by itself. And we're going to get a value to 2 decimal places of 9.51 liters of gas. And so we went from a 500-liter container of gas to just under 10, which is what we would expect when we increase the pressure by so much. Even though the temperature changed, and that would affect the pressure and the volume as well, the biggest factor here is the fact that the pressure changes. So this almost becomes like a Boyle's Law problem, where as the pressure increases by a lot, the volume would decrease by a lot. And so our final answer of 9.51 liters makes sense. If we press that gas way down, we would expect that its volume would decrease over time. So I hope that that's helpful. Using this combined gas law equation can help you solve any of the problems that we've done so far related to gases, as long as moles are involved. We'll get to that in a moment. And I hope that this is helpful. So feel free to reach out with any questions, and have a great day.